More than 10 million people around the world believe the Earth is flat, not as a joke, but as a serious scientific claim. They question satellites, space agencies, even gravity itself. So today, we're not here to mock anyone. We're here to test the strongest flat Earth arguments and see what reality actually shows us. At first glance, to many people, the idea of a flat Earth doesn't sound crazy. In fact, to many people it feels intuitive. When we stand on the ground and look around, the world appears flat. The horizon looks like a straight line. No matter where you are, at the beach, on a highway, or in an open field, you don't see a visible curve. Your everyday experience tells you that the surface beneath your feet is level and unmoving. This is one of the strongest reasons people question the shape of the Earth. Human perception is built on what we can directly observe, not on abstract measurements, and from our point of view, the Earth simply doesn't look like a spinning sphere. Another common argument is eye level. When people look at distant objects, they expect them to remain at the same height. If the Earth were curved, they assume objects should drop far below their line of sight. But in many cases, distant buildings, ships, or mountains still seem visible, especially with zoom lenses or binoculars. This creates confusion. If the ground is curving away, why do these objects still appear where we expect them to be? Then there's aviation. Airplanes don't appear to constantly tilt downward during flight. Passengers look out the window and see a stable horizon. Pilots don't announce that they're adjusting the nose of the plane to follow a curve. To many people, this feels like strong evidence that the Earth isn't curved at all. From the inside of a plane, everything feels steady and level. There's no sensation of spinning at hundreds of kilometers per hour, no feeling of motion that would suggest the Earth is rotating beneath us. All of this feels convincing because it aligns with human-scale experience. We judge reality based on what we can see, feel, and sense directly. Large-scale phenomena, like planetary curvature or rotation, don't easily register in daily life. So when someone says the Earth looks flat to me, they're not being dishonest. They're describing their experience as a human standing on a massive planet. And that's the key point. Flat Earth arguments don't start with science, they start with perception. The real question isn't why these ideas exist, it's whether our everyday perspective is enough to describe the true shape of the world. That's where testing begins. To understand the shape of the Earth, we don't need complex equations or advanced technology. We can start with simple observations that anyone can verify. One of the most common tests involves ships at sea. When a ship moves away from the shore, it doesn't simply get smaller until it disappears. Instead, the bottom of the ship vanishes first. The hull drops below the horizon, while the mast and upper structure remain visible for longer. If the Earth were flat, the entire ship would shrink evenly as it moved farther away. But that's not what we observe. This effect has been documented countless times, using binoculars, telescopes, and modern cameras. Height provides another important clue. The higher you go, the farther you can see. From the top of a building, a mountain, or an aircraft, the visible horizon expands. Objects that were hidden at ground level become visible again. This behavior matches what we would expect on a curved surface. As your viewpoint rises, your line of sight clears more of the curve. On a flat surface, gaining height wouldn't reveal anything new. Distance alone would determine visibility. Flight paths offer another practical test. Commercial airplanes do not fly in straight lines on flat maps. Instead, their routes curve, especially over long distances. These curved paths make sense when plotted on a globe. They represent the shortest distance between 2 points on a spherical surface. On a flat Earth map, many of these routes appear strangely inefficient or even impossible. Finally, there is gravity. Every object with mass attracts other objects. This force pulls matter toward the center of the Earth, creating a roughly spherical shape over time. When we drop an object, it falls straight down toward the center of mass beneath us. Across the entire planet, this direction changes slightly depending on location. That behavior is consistent with a curved surface, not a flat plane. None of these observations rely on authority or belief. They rely on repeatable tests and direct measurement. Each one, on its own, raises questions. Together they form a consistent picture. Testing doesn't begin with assumptions, it begins with observation. And when we test these claims against reality, the results point in the same direction. Flat Earth theory may seem to fit some casual observations, but there are many real-world phenomena it cannot explain. One of the clearest examples is time zones. The sun rises and sets at different times in different parts of the world. On a flat Earth, the sun would illuminate all areas simultaneously, making local noon impossible. Yet in reality, when it's midday in New York, it is night in Tokyo. This simple observation aligns perfectly with the rotating spherical Earth. Seasons are another phenomenon that flat Earth models fail to account for. Changes in temperature, daylight length, and the sun's angle throughout the year are caused by the tilt of Earth's axis as it orbits the sun. On a flat Earth, both hemispheres would experience the same season at the same time. But in practice, when it's summer in the northern hemisphere, it is winter in the southern hemisphere. This predictable pattern directly reflects the geometry of a tilted, rotating sphere. Global navigation relies heavily on a spherical model as well. GPS satellites orbit the Earth in precise paths, transmitting signals that allow accurate positioning anywhere on the planet. If the Earth were flat, these orbital systems would not function as they do. Planes, ships, and smartphones all depend on the curvature of the Earth and its gravitational field for navigation. Finally, we see this in the paths of the sun and stars. The sun's rising and setting angles shift throughout the year, and stars visible from one hemisphere are not visible from the other. A flat surface cannot account for these directional changes, the consistent positions of the North Star, or the rotation of the constellations. These patterns repeat reliably year after year, providing clear evidence of a rotating spherical Earth. In short, flat Earth explanations can mimic some basic observations, but they break down when tested against larger consistent patterns. Time zones, seasons, satellite systems, and celestial motions all rely on a spherical Earth to make sense. When we observe reality closely, these phenomena point in one direction, toward a globe. No model based on a flat plane can account for all of them simultaneously. Science works by asking questions, making observations, and testing ideas against reality. It doesn't depend on beliefs, traditions, or what someone claims is common sense. Instead, it relies on repeatable experiments, measurable data, and consistent patterns. When we look at the Earth, the evidence points clearly in one direction. Time zones, seasons, the paths of satellites, the movement of the sun and stars, and even the way objects fall, all of these phenomena align with a spherical rotating planet. None of them make sense on a flat plane. Importantly, science doesn't dismiss questions or curiosity. Flat Earth ideas, while incorrect, often begin with simple observations that anyone can notice. The horizon looks flat, objects appear level, airplanes seem to fly straight. Science welcomes those observations, but it tests them further, Going beyond what feels intuitive, it asks, what does reality actually show? This approach, observing, measuring, testing, is why scientific conclusions are reliable. They are not perfect in a single moment, but they become stronger as multiple independent lines of evidence converge. And when we examine the Earth from different perspectives, the evidence consistently points to the same reality. We can respect people's curiosity and questions while still looking honestly at the results. Reality is not about winning an argument or proving someone wrong. It's about understanding how the world actually works, based on facts and observation. So, when we step back and consider all the evidence, the conclusion is clear. The Earth is a globe, rotating and orbiting the Sun, following the same physical laws that govern the rest of the universe. Observing carefully, testing consistently, and thinking critically, this is how reality wins every time. By trusting in evidence rather than assumptions, and by letting observation guide understanding, we can explore the universe with confidence. And that is the lasting lesson. Curiosity is valuable, but facts are what reveal the true shape of our world.